Hi, in this video we'll talk about refracting prisms. These are very special kind of prisms where a lot of total internal reflection happens and they behave in a different way by just changing the direction of light and so on and so forth. So here, for example, we have a isosceles prism. So these three prisms are basically same. So we can show that something like that here. So 60 degrees and so all these prism in A, B, and C are the same. So this is 45. So this is 45. This is 90 degrees. And they are shown sort of in a different orientation. So in the first case, the light is coming from this direction. This is case A. In this case, case B, the light is coming from this side. This is case B. And case C is when the light is coming from this side or that side. So that's case C. So they are the same prism, and we'll observe that a lot of total internal reflection happens once or twice, which means that the energy is getting passed through this prism without any loss, and hence these are a very special kind of prism, and they work on the basis of total internal reflection. So first thing first, here prism number A, basically the light is coming like this. As we know from the physics that no reflection will happen over here, light will come here, and we have a total internal reflection here, hence the light is going like this. Similarly for the ray number 2, no reflection here, come here, total internal reflection, here no refraction, total internal reflection, so on and so forth. So this one basically changes the direction of light by 90 degrees. So it was coming like this, now it is going like this. In this case, it actually reverses the direction of light, so it was coming like this, now it is going like this. So by 180 degrees. Here the direction of light is same, but it actually inverts the image. So if this is the image, so this is the light coming like that, so it will become inverted. So if you want to invert something, you can use this prism in this direction and you will be able to invert the image. This is another case, and it is a case where shown that a combination of two prisms like that are getting used in a periscope. Now what is important is that a total internal reflection is happening within the prism, okay, and we need to derive condition for that, right? So why this is happening, at what condition it will happen, and that's what we will try to observe and achieve in this video. So the first two cases where the light is coming like this and this are very interesting and actually different from the case number 3. So let's take the first two case here. So we have a light coming like this, getting totally internally reflected once and then going back. In this case, totally reflected here, then here twice and going back, and here is the change of direction. And we are going to derive a simple equation which will suggest that how the light is getting. We know that this is 45 degrees, okay, this is also 45 degrees, and this is 90 degrees, okay. So now the ray of light is coming like this, hitting the prism here. So we have a normal, okay. This alpha is going to be our angle of incidence for this interface, okay. And we can always write a Snell's law for a total internal reflection condition, which will be ray of light is coming like that, getting reflected at the same angle alpha, getting reflected like this, and this is 90. So by physics we know that we can write that equation. So let's do that. So basically the index of refraction or refractive index of the prism is n into sine of alpha is going to be equal to 1 into, which is the refractive index of the air, sine 90, which is also 1. So this is 1 sine of alpha. Now for the total interreflection to happen, basically the sine of alpha has to be greater than 1 by n. That we know, and that we proved in the video where we discussed total interreflection. Now we know that alpha here is basically 45 degrees, right? So we can write the equation again. So sine of 45 is greater than n. Now for the n has to be greater than sine of 45. and sine of 45 is basically 1 by root 2. So in all the cases, if the for this kind of prism, basically if it is happening, if the n is more than root 2 or n is greater than 1.414, we will observe total internal reflection at these interfaces. Okay, same here, right? Now you can see that these are very symmetrical prisms, right? So just copy paste it in the direction. Same here. So if we have n greater than root 2, we'll have total internal reflection here. Okay, so the point to remember and understand that in case of isosceles prism with 45, 45 and 90-degree angles, n is has to be greater than under root 2, and it will have total reflection, and the prism will work like a mirror. Now in case 2, now this is interesting because here we can find out that what is that number, what is the value of n for which total internal reflection will happen. Okay, this number will be different because the angle of incidence is different and we have two refraction happening over here. So when the ray of light is coming like that, first thing first, it is getting refracted. Here, after that reflection, the total internal reflection is happening. Okay, and then it's going there, and then the reflection is happening. So let's work that out. What will be that angle, or what is the condition under which for the value of n? So we are just interested in the value of n. For what value, sorry, of n you have total internal reflection. Okay, DIR. So I've just put it drawn a little bit bigger diagram to understand. So the ray of light is coming like this, and we know this is 90 degrees and this is 45, right? Again, this is 90, so hence this has to be 45. So the angle of incidence, this is 45, this is 45, and this is 45, right? So angle of incidence here at the origination, when visiting the prism for the first time, I is equal to 45. And we know that we can write that equation of Snell's law at the point C. Now it is getting reflected. So from the normal, this is beta, which is angle of refraction. What? Now the ray of light is coming like that, hitting here. We don't know these angles, we are calling it alpha, and then again getting reflected. So we know this angle is going to be also alpha, and then some reflection is happening. We are interested in finding the total internal reflection happens at point D, and that is what we are looking for, right? So definitely we can write Snell's law here, here as well as here, right? So let's begin and try and write Snell's law for the point number 1. So which is point C. So we know that one, which is the refractive index of air, sine 45 is going to be equal to n into sine beta. Okay, n is the refractive index of this thing, and everything we want to put in terms of n because that's the only known quantity. Sine 45, we know that sine beta is going to be it's fine. Now let's write the equation here, which is the total internal reflection condition, and we know we have this angle of incidence alpha in the refractive index n, so we'll say n into sine of alpha is going to be equal to refractive index of the air is 1, and this is getting totally internally reflected, so this angle is 90, so 90 is equal to 1, sine of alpha is going to be equal to 1 by n, and for the total internal reflection to happen, it's the same equation like we obtained last time, has to be greater than 1 by n. Now we have to just find sine alpha in terms of n, and then we will be done, right? To that, basically, we know that we can find a relationship. We can find a relationship between beta and alpha. If we somehow geometrically find a relationship between alpha and beta, we can reach out to n. So we have this alpha here, right? It is connected to beta, and the beta we have already connected to n. Okay, so if we are somehow able to find a relationship between alpha and beta, then we can relate and write this equation in terms of n, and then we'll be done. So let's try and find that relationship between alpha and beta geometrically, and that will help us solve the problem, right? So as you observed, this is how to think, right? So we wrote the what we can write from the physics, the Snell's law at these 2 points, and we need to find the condition, what will be the n, right? For which the total reflection will happen here. The unknowns are basically alpha and beta. We are able to write beta in terms of n, which is a good thing, and now alpha in terms of n. And if we can find a relationship between alpha and beta, we'll be able to write a better equation only in terms of n. That's what we'll try to do. Okay. Now look here. This is alpha. So this is 90 minus alpha because this is perpendicular. Okay. Again, this is 45. Okay, this is 180 minus 45. Okay, that much we can write. Then we add that up, 90 minus alpha and with beta, right? It will be equal to 180. Okay, so this one will get cancelled, and this will be something like 90 minus alpha plus beta minus 45 is going to be 0. 90 minus 45 is going to be 45 minus alpha plus beta is going to be 0. Now we have alpha is going to be equal to 45 degrees plus beta, right? So by simply observing the property of a triangle, we are able to arrive at the equation which we are looking for, the relationship between alpha and beta. Okay, that's very cool. So now let's plug in there sine alpha. Okay, so we have this equation, sine alpha has to be greater than 1 by n, right? That is our condition for total internal reflection. We're going to put it there. Sine 45 plus beta total by n. Now this is where we're going to use trigonometry. We know that sine A, sine B, sine 45 cos beta plus cos 45 sine beta whatever 1 by n. Sine 45, and this thing is under root 2. This okay. So far so good. Now we need to just plug in for beta and with a function of n, and we'll be done. So we know the sine beta is 1 by root 2n. Okay. So sine beta we have already derived, so we will plug in there. Cos is going to be simply under root 1 minus sin square beta, right? Sin square beta, and cos 1 minus 1 square greater than root 2 by n. Now see, now we have everything in terms of n, and we just need to find and solve this equation to find the condition for n. As you can see that, you know, when we started try to solve the problem, we basically wanted to know the for what value of n the prism will have the TIR, right? So TIR is a condition when the ray of light will get totally reflected over here, and somehow we managed to find the relationship between alpha and beta and basically arrive at an equation which only has n, right? So that is important, how to think about a problem when you're trying to solve it. Now let's further simplify this. Okay, so let's take this upwards. So I'm going to do okay. That will happen first, which we can take out as a common 1 plus under root 1 square minus 1. This has to be greater than 2. Okay. Take it to the side. We basically have a very simple equation here now. It says that 1 plus 1 square has to be greater than root 2 into root 2, and then 1 square minus 1 has to be greater than 1. Right? Now, for that to happen, basically the n has to be greater than. So, in any case, when we have n greater than 1, basically this condition which we derived in terms of n for total internal reflection to happen on the base of the prism, right? So, this is our condition for total internal reflection to happen at the base of the prism, which is an isosceles one. As we mentioned, the ray of light is coming like this. It's 45, 45 is 90. Right, so total reflection will happen here if the n is greater than 1, which is wonderful because anything which is not vacuum has an n greater than 1. So it does not matter basically which material we use, basically we'll always have a total reflection happening over here. The ray of light is going to go like this. Okay, so amazing result with this. So to recap, basically we have 3 cases of reflecting prisms as seen over here. So these are the same prism, basically the isosceles prisms, right? So if you're sending the light on this, basically you have a 90-degree deviation, sending the light like this by 180 deviation, and you have a condition that basically the n has to be greater than under root 2, and you will have this total internal reflection happening, and you will expect the direction of the ray of light to change, and there will not be reflection. In this case, however, for any material, basically, you will have total internal reflection happening, and the ray of light is going to invert the image, which is amazing. So with this, we are going to close the video, and in next video, we are going to move and actually look at more optical instruments like this, where we can use this concept of law of refraction in detail. As I said, you do not worry about much about calculus, just get the concepts right, and that will help you out in the long run.